Suma, shall I proceed?
Yes, sir.
How many joined?
5 students, sir.
Shall I start then?
Yes, sir.
Yeah. Once again, good morning to one and all. I welcome you all again for the GATE 2021 coaching under Prerna scheme. So we have started 2 weeks back. On the first week, only 1 hour we have taken. On the day, we just explained what is the strategy and what is the basic syllabus of the GATE and what is the syllabus for the strength of material. So strength of material, as you know, I am dealing for the both civil and mechanical students this time. So this is one of the important course for both civil and mechanical, but especially for mechanical engineering students, around some 10 to 12 marks it may cover in GATE examination, as I already mentioned in the previous classes. So today what I'm going to do, yeah, last week what we have covered, that is again with notes form, with the thoroughly like few definitions I just wanted to cover, like basic things, like what is meant by strain energy, like when you move to the stress strain diagram for the mild steel and even other type of steels, even Poisson's ratio, elastic modulus, like this. Especially, I would say, once again, I would like to cover thoroughly on simple stress and strains, because simple stress and strains is the main chapter to understand the future chapters, means further whatever we are going to discuss in the whole syllabus of the strength of material. So that is why I would like to give more stress on strength of simple stress and strains. In addition to that, I would like to show the GATE material, which is provided by ACE, Association of Civil Engineering, the old version I have, so that I can show you even step by step, like snapshots in the PPT. So please bear with me for 2 hours. So you are going to get a lot of knowledge. So please inform to your friends once again. Classes are going well, and faculty members are very interestedly they are conducting the GATE classes. please ask them to join in time, and number of students also should come forward, because don't take that this is a free mode, whether we are attending or not, no one will going to ask us like that. Please do not misuse. Once again, I'm requesting you all. So of course, indirectly I'm suggesting you all, it's a one golden opportunity for you to crack the gate examination. Whatever, maybe you may get little bit knowledge, that knowledge also you should not leave. So but according to me, I can tell you 100%, I am preparing very good notes, and I am collecting different materials from different sources. Even I am trying to explaining in very elaborated way what I have seen and what I have learned in the different places, like my BTech time and even my MTech in IIT Guwahati and PhD from IIT Madras. So I have seen the coursework time, how the faculty members, the professors from IITs that they taught. So from there we enhanced some knowledge. So that knowledge I wanted to transform you all. So that's why I have interestedly I came forward to take this course. So please make use of this opportunity. Please do not misuse. Once again, I would like to show the syllabus of the strength of material, that is simple stress and complex stresses, which is already shown in the last class. Even in the writing form, I have written here the introduction, strength of material introduction, stress, SFD and BMD, principal stress and stress transformations, bending, shear stress, deflection, theory of failures, torsion, pressure vessels, column and springs. Okay. So when you talk about the introduction, as I already shown you, solid mechanics is basically divided into two things. One is rigid body analysis, another one is the deformable body analysis. So rigid body analysis basically, if you talk about the engineering mechanics, so with example it has been explained here. The molecules are not remains in the same place. It is not changing the distance. For suppose if you see the L dash is the sorry, L is the A to B molecules distance, whereas A dash and B dash is the again L dash. So L dash equals to L, so that remains same place. That is why this is to call it as a rigid body analysis. If the distance between 2 points within the body before and after the application of the load remains constant, then body is said to be rigid body. Basically, we deal these rigid bodies in engineering mechanics, which is already studied in first year. That is of course already in the last class I told you, but in thorough way, I just want to explain once again your basics. Deformable body analysis. Here L1 is the A dash B dash distance. So L1 is not equals to L, because this is a deformable body. When you apply the external load on the body, the A dash and B dash distance is getting changing due to the deformable nature of the body. If the distance between 2 points before and after the application of load changes, the body is said to be deformable body. So this is what we are going to see now, strength of material. Again, deformable body classified into 3 categories. First one is elastic body, plastic body, viscoelastic or viscoplastic body. Okay, so elastic body means you can see when you apply the load, this will try to deform. Okay, at T equals to T at the time of T equals T. So the elastic body regains in original shape after removal of the load. That is called elastic body. Plastic body means a plastic body does not regains its original shape after removal of load. That is means by plastic body. Viscoelastic means viscoelastic basically it has high deformation. Basically, viscoelastic it has high deformation, especially like bitumen, asphalt. We used to mention it as a viscoelastic materials. And for example, if you say there is a ferrous means basically steel, iron, MP means melting point. So at the 1539 degrees Celsius, if you melt it, the elastic body always will be less than melting point by 2. Melting point by 2. And whereas viscoelasticity body, melting point by 2, it will be always greater actually. So that you can say viscoelastic body. Of course, the example also I have to mention to you. Bituminous it has very high deformation. An elastic deformable body. Elastic deformable body means this one. So in this elastic deformable body, again linear elastic body and non-linearly elastic body. So linearly elastic body means Hux's within proportionality limit will be there. That means stress proportional to strain follows Hux's law, whereas non-linearity elastic body means do not obey Hux's law. So the example for the linearity elastic body is, you can see the mild steel, uh, and this slope is 1 degree basically, and this sigma is stress and epsilon is strain, and PL is proportionality limit. So up to proportionality limit, the stress is proportional to strain. It obeys the Hooke's law. Whereas another one is rubber. This is the best example for non-linearity elastic body. Sigma and epsilon, if you see, it is not at all proportional to in any level. You can see this. Sigma is not proportional to epsilon. So what is the note here? Important note here. Strength of metal is studied for linearly elastic deformable bodies only. Okay, we are not looking after the non-linear elastic bodies under the strength of materials subject. And if you see the deformable body, or it's nothing but a failure. Again, these are divided into two things. One is yielding and another one is fracture. In yield failure, cracks are developed before getting actually failed, giving the indication of failure. This is actually very like healthy thing, I would say, because before failure of the any structural member or any bar you take or rod you take, if it is giving warning, you will be stopping the experiment, or you will be away from that catastrophic failure, because at the end, actually in the breaking point, it may give a lot of sound, and it may break, and it may even fail, like catastrophically fails, and it may causes the injury also. So that you can avoid by welcoming this kind of failure. Of course, this kind of nature of the failure only you always expect for the any type of structure. Suppose being as an engineer, you are designing one building, and you always prefers to design your structure under this category of failure only. So best example for yielding is ductile material, whereas fracture is it doesn't give any warning actually. So it's nothing but a brittle nature of failure. In fracture, no cracks are developed. Material fails suddenly without giving any indication. Maybe a mechanical student may not understand, which I am going to give now example. For ductile material, RCC, reinforced concrete, whereas brittle material, PCC, plain concrete. So plain concrete will not give any cracks. Suddenly it will fail at the center with the catastrophic failure, sudden failure. Whereas steel, RCC, that means reinforced cement concrete, will give warning, very ample warning, because of the steel provided at the tension zone. Before it fails, it will try to yield actually, because basically steel, as you know, that it will yield, it won't fail suddenly, and it will try to make plastic hinges if possible. If possible means that is depends on your type of load application. If you are applying the cyclic load or any type of static load, it will try to create the plastic hinges in the steel, and plastic hinges indirectly it will help us to not give the sudden failures of the members. So I hope you understood the basic difference between yielding and fracture over here. And the yielding best example is ductile material, and brittle material is for the fracture. And first of all, and what is meant by ductility and brittleness? Property by virtue of which it can be drawn into thin wires. Here in this ductility, whatever that the sigma UC, okay, sigma UC means its compression. Normal, sigma is normal, U is ultimate, and C is compression. And here UT means ultimate tensile, and here is stress. That means for ductility type of structures, compressive strength will be higher than tension, even higher than shear. At the same time, tension will be higher than shear for the ductility kind of materials or even structures. I hope you are understanding what I'm trying to explaining here. The compressive strength would be higher than tensile strength, even shear of that particular member or particular structure for this ductility nature of the material or member. Okay. Whereas in the brittleness, lack of ductility is brittleness basically, and here the compressive stress only will be higher than shear only, but tensile strength will be again lesser than shear. Okay, are you getting my point? So shear, it will be higher than shear only, whereas we can't say here in the ductility this member will be higher in compression. We can't say this will be higher than shear. Maybe I wrongly mentioned. We can't say this will be higher than shear. So sometimes shear may be higher than even compression, but obviously tension will be higher than shear actually. Okay, so that is the nature of the ductility, and the brittle nature it will be higher than shear, but we can't say compression will be higher than tension. So since the material is weak in tension, it fails on a plane subjected to maximum tensile stress. See, so brittle nature basically it is very weak in tension. So when it reaches the maximum tensile stresses, that fellow will try to fail actually. Since the material is weak in shear, it fails on a plane subjected to maximum shear. Okay. Are you getting my thing? Because finally, this is only the drawback. This is only the drawback which I rounded here in this particular materials, both in ductility and brittle nature. So this has been clearly mentioned here. You can understand this. Then higher the ultimate strain, more the material will be ductile. When you have the ultimate strain is higher, ultimate strain is higher. Strain means what? Change in length by original length. So if change in length is more, obviously original length, say you have a 1 meter, change in length you have a 10 centimeters. 10 centimeters is nothing but a 0.1 meters. So 0.1 divided by 1. Obviously you are maybe getting like 0.001. Okay. So that means what? It has very higher ultimate strain. So ultimate strain, if it is higher, the ductility is also very higher. Even the definition of the ductility, I would say, yield ultimate strength by yield strength. Ultimate displacement by yield displacement. Ultimate displacement by yield displacement. That means one member, if you take maybe rod or maybe any concrete member, or maybe you take any brass or aluminium, when you're testing under the UTM, universal testing machine. So if it is giving very higher deformation and it is still not failing, it is keep on showing deformation only. And okay, and it will show the yield deformation also. Yield deformation means maybe in the graph, if you observe, maybe at one point at the yield load, whatever the respective displacement in the P delta curve, whatever the respective displacement, that is yield displacement. So the definition of the ductility for the P delta curve is nothing but a ultimate displacement by yield displacement. Okay, so from that ductility you can represent. So that is only it is showing higher the ultimate strain, more the material will be ductility, and greater the ultimate strength of the material, more it will be brittle. That means for any material, if strength is very higher, that member would be very brittle nature it has. That means it will be like a very hard kind of rock, and it won't deform, it won't show any ductile nature. Suddenly it will fail when you apply the load, but it will try to take maximum load actually. And you can see here there is a graph and B graph, and this is ultimate stress and ultimate failure strain at A, and this is for B, respectively. And now you see which one will have more ductile. B is more ductile than A. Obviously, no, because you see this is the ultimate strain, whatever I have mentioned in this definition, the ultimate strength for B graph is higher. Then obviously that B kind of graph, B kind of metal only will have more ductile. But if you see strength wise, A only has more strength. Okay, then A is more brittle than B. Obviously, because the ultimate strength of the A graph is lesser. So like that, you can easily understand the definitions and the basic concept behind the yielding and fracture, and of course, in turn, it will belongs to it will become ductility and brittle nature. And assumptions in the strength of metal is these are of course already last class I have shown, but very quick way I have shown. But here you can easily observe and you can easily understand. The body is deformable first of all, and it should be continuous. And the body is homogeneous and isotropic. So what is meant by homogeneous and isotropic can be seen here. One side E and another side is E1. If the elastic properties at all the points within the body in one particular direction is same, then metal is homogeneous. Are you getting my point? Along the x direction, the E is constant. Along the vertical direction, E1 is constant. Otherwise, vertical side also maybe that may be E, or even horizontal side also that may be E1. It doesn't matter. But in one direction, particular direction, the metal properties are very same, equal. So that is why it is a homogeneous kind of thing. Best example, steel actually, entire cross section or entire section, if you see the metal property, the molecule spreading and the distribution of the inside all particles will be equal, same. So best example for homogeneous is steel. Then isotropic. Isotropic means sorry, if the elastic property in all the direction at a point within the body remains same. If the elastic property in all the directions at a point within the body remains same, then the metal is said to be isotropic. You can see in different directions, but from one point that all metal properties same actually. Okay. In all places, if it is one side is E and one side is E1, it cannot be isotropic actually. But in all directions, the metal property is E1 only. So even at the bottom, if you see this is E2, and this is the best example for isotropic. And if you add these two together, homogeneous and isotropic, you can see this. If the elastic property in all the direction at any point within the body remains same, then metal is homogeneous and isotropic. Within the body only, it should be equal in all directions for the all directions within the body. So that is nothing but a combination of both actually. So this is homogeneous plus isotropic. And third point is, before going to third point, anisotropic means what? In all directions, the metal property will not be same. You can see this. E1 is there here, E2 is there here, E3 is there, E4 is there. So that is called anisotropic. And orthotropic means in three directions, the major directions of three directions, X, Y, Z, the global directions, the metal property will be different, but it has one particular directions, particular coordination actually. So that is X coordinate and Y coordinate and Z coordinate. So like this, if it is there, then you should call it as a orthotropic. And now third assumption of the strength of metal is consider only surface force and self weight or dead load of the member. Okay, surface force only, and self weight and or dead load of the member is neglected. In generally in all strength of metal, whatever the bar or rod it is coming, you must focus on try to neglect the self weight or dead load of the member. That means there is a member. If you take like this, when you are applying the tensile force P, And what is this W? Mg. W is nothing but a mg, correct? Mass into g, acceleration due to gravity, correct? It is nothing but a W, self-weight of the member. Due to gravitational force, it is always downward actually. Then what is fourth one? Engineering stress and strains are considered, whereas true stress and strain are neglected. Okay. Engineering stress only we need to consider engineering strength of materials, and true stress and true strains are we are neglecting. Okay. And you can see this. There is a bar with the cross-sectional area A, and when you apply the P load, and the cross-sectional area is reducing into A dash. Okay, A at T equals to 0, whereas A dash at T equals to T actually. Okay, with some time it has transferred. And what is meant by engineering stress? So engineering stress is nothing but a load by initial area. Load by initial area means before applying the load, whatever the area is there, that area only you must consider. That is called engineering stress. It is not that after applying the load in the area there are changes. Like what is that? Instantaneous area. That means after applying the load there is a changes in the area that you should not take. Of course, that is a true stress. Obviously, why it is true stress? Stress is an internal resistance offered by a body. After application of the load only, stress is coming due to the strain. Okay, I hope you are understanding the concept. Stress is depending on strain actually. How it is coming? When you are applying the load only, it is coming. Okay, so that you must understand what is meant by true stress. Of course, why into mark it is, as I already mentioned in the assumption, true stress cannot be considered. Okay. Superposition principle is valid because Hooke's law is valid. Okay. Superposition means you can see superposition principle means whatever that how many loads, whatever loads you apply P1 and P2. When you apply P1, delta 1 will be comes, and when you apply delta 2, P2 and delta 2 will come. When you apply both together P1 and P2, delta will come. So the delta is nothing but a delta 1 plus delta 2. Okay, that is the whatever the loads you apply. Even superposition principle, I told that any type of load will be give the same effect on your structure. Any type of load, it may be a concentrated load or uniformly distributed load, uniformly varying load. It will give the same effect. And you can even see, you can see this. For the this is one mild steel behavior of the load versus displacement diagram. When I apply the P1, the respective delta 1 is like this, and when I apply P2, and the respective delta 2 is this. If load of P1 plus P2 is applied, then the deflection is delta 1 plus delta 2, and B1 is B is delta 1, and C is delta 2, and D is cannot be determined. So this is one kind of question. One kind of question it is mentioned here. But generally, if load of P1 and P2 is applied, what is supposed to come? Delta supposed to come actually. But from this diagram, from this experimental study, or from experimental work, if you observe, the options are giving only delta 1 plus delta 2 and delta 1 plus delta 2. Like this, but what is the answer here cannot be determined actually when you apply the P1 P2 like this, because the what I would say resultant delta cannot be find here correct exactly. So that is the answer for this kind of questions. And another one is material is prismatic. Material is prismatic, that means uniform cross section throughout the length. No residual stresses. That means after applying the removal of load, some stresses are there inside like that. It won't be there. No residual stresses. Then come to the factor of safety. So factor of safety means like if you take the ductile material, lower yield point is this, and this is breaking point. So factor of safety is nothing but a lower yield strength by working stress. Okay, factor of safety is always greater than 1. Factor of safety is always greater than 1. It cannot be less than 1 actually. For brittle material, if you see, there is no that kind of behavior what I have shown in the previous diagram. There will be finally ultimate strength actually. So there is a factor of safety equals to ultimate strength by working stress. Here, lower yield strength you will consider as a your numerator, and denominator working stress. For the brittle materials, ultimate strength only you have to consider divided by working stress. And in industries actually factor of safety is generally 1.624. Okay, factor of safety అంటే బేసికల్ గా స్ట్రెస్ కాన్స్టెంట్ గా ఉండి ఎప్పుడు హైయర్ గా ఉంటుంది. ఈవెన్ స్ట్రెంత్ కూడా ఎప్పుడు హై ఈజ్ లెస్ దాన్ 1.6. స్ట్రక్చర్ విల్ నాట్ బి డ్యూరబుల్ యాక్చువల్లీ. ఈ ఫ్యాక్టర్ ఆఫ్ సేఫ్టీ ఇస్ మోర్ దాన్ 4 ఉంటే ఈ వాట్ ఎవర్ ద ranges are there 1.6 to 4. If it is less than 1.6, the structure will not be durable. If it is more than 4, structure will be uneconomical because either higher quality material will be used or more amount of lower quality material will be deposited at the surface. Okay, anything may happen, so it leads to danger actually. Then come to the another very important definition, strain energy. Strain energy means what? Strain energy means it is energy stored within the deformable body due to work done by the externally applied load on the body. It is energy stored within the body, within the deformable body due to work done by the externally applied load on the body. That means if you apply some load on the any member or structure, whatever the work done is there, that process called work done. Okay, in the deformable body, whatever the energy is storing, that means the energy, due to energy, that body is not getting deformable much, but it is deforming but not deforming much due to external force. That is called kind of strain, because change in length by virtual length is the direct definition of the toughness and modulus of toughness. First of all, toughness, it is basically due to impact load. It will happen impact load, sudden load. Okay, toughness is nothing but it is the strain energy stored in the deformable body due to impact loading just before failure or fracture. Even you can see the one load versus deformation diagram is there. Area under the P delta curve is nothing but a toughness. Very clear. Once again, this is an interview question, this is a gate question, IS question, even objective type. So many places this question they used to try to ask. Toughness is nothing but a area under P delta curve. What is meant by modulus of toughness? It is the strain energy stored in the body per unit volume of component due to impact loading just before fracture or failure or fracture. Okay, MOT equals to toughness by volume of component. Okay, area under stress versus strain. Okay, area under sigma versus strain curve is nothing but a MOT. You can see this. The difference between toughness is area under P delta curve, whereas modulus of toughness is area of sigma epsilon curve. In general, greater the toughness, more the ductility, and vice versa. In general, greater the toughness, more the ductility. Toughness ఎక్కువగా ఉంటే డక్టిలిటీ ఉంటుంది, అండ్ దానికి వైస్ వర్సా. టఫ్నెస్ తక్కువగా ఉంటే డక్టైల్ గా ఉంటుంది. ఓకే, ఈవెన్ టఫ్నెస్ ద మీనింగ్ ఇట్ సెల్ఫ్ ఇట్ ఈస్ గివింగ్. అండ్ ఈవెన్ యూ కెన్ సీ దిస్ A and B curve is there. You have areas here like this. But ultimate strains are there. Summation of FA failure ultimate strain less than ultimate strain in B curve. But B is more ductile, correct? Because higher ultimate strain is there, and in addition to that, it has more area also, more toughness also. Also area under P delta curve, AA less than AB. B is having more toughness than A. That is correct only. Okay. Next, then another definition is resilience. What is resilience? When you see the P delta curve, when you're applying some load, the curve has been formed for the mild steel. You say this is the elastic limit point. Before elastic limit point, if you consider some point at P and respect to delta, area under P delta curve is nothing but a resilience. It is the strain energy stored in the body due to static load actually within the elastic limit. Elastic limit lo undali, but static load, not impact load. Impact load ante toughness. Static load ante resilience. But up to under the again elastic limit lopale undali. Proof resilience means again P delta is there and area under P delta curve equals to proof resilience. But up to what point you can see? It is the strain energy stored in the body due to static load up to the elastic limit. Not before elastic limit, up to the elastic limit, whatever the load if you take, that is a proof resilience. Then modulus of resilience means it is the strain energy stored in the body due to static load up to elastic limit per unit volume of component. That means MOR equals to proof resilience divided by volume of the body. That is called modulus of resilience. It is clear? The all definitions are clear? Very, very clear. Next, equations for resilience. First of all, if you talk about the assumptions, number one, all the external work done is stored in the body in the form of strain energy. All external work done is stored in the body in the form of strain energy. There is no loss of energy. And elastic limit, proportionality limit, and yield limit are considered to be same in the resilience point of view. And it is a linear curve. Stress at elastic limit only, it's a yield stress. Elastic limit, proportionality limit, yield limit, everything is same. Okay, and area under the before the ELR, PLR, EL, that YL, that is nothing but a resiliency, as you know. So resilience must be measured with U, denoted as U, equals to the area here. It is looking like a typical triangle. So half into P into delta is nothing but your resilience. Hooke's law is valid for this resilience, and stress is proportional to strain actually. It's not a Young's modulus, it's a strain. So stress is P by A and P is sigma into A, correct? Strain is delta by L, change in length by original length, and delta equals to epsilon into L. Put 2 and 3 in 1. In P and delta you found, and if you put this everything into 1, half into sigma A, this is, delta L is this is, and finally sigma into epsilon if you write here, and A into L if you write together, and volume of component is nothing but A into L. So therefore U equals to half into sigma into epsilon into V volume. So finally resilience can be written like this also. Okay, then now sigma equals to Young's modulus into epsilon can be written So epsilon equals to strain equals to sigma by Young's modulus. So if you put 6 in 4 now, okay, in the 4 if you put 6, u equals to sigma square by 2e into v, correct? How this formula is getting developing. And put 5 in 4. If you put 5 in 4, you are getting the equation here, u equals to half into e into epsilon square into v, correct? Then proof resilience can be written like this: u equals to sigma y square divided by 2e into v. Okay, modulus of resilience equals to proof resilience. Proof resilience has been written like this. Proof resilience, why it has been written like this? Proof resilience is nothing but a, as I told you already, proof resilience is nothing but a load up to actually elastic limit. So elastic limit means you can take it full yield up to yield. This is actually before yield point. That is why it is not mentioned here sigma y. Here only sigma. But whereas here sigma y it is because it is up to yield point actually. That is why proof resilience is getting like this. And your u is like this, and modulus of resilience, volume is coming in denominator, and numerator volume and denominator will cancel, and finally sigma y square by 2 is nothing but your modulus of resilience. Formulas: now u equals to half into p into delta, half into sigma into epsilon into v, e into epsilon square by 2 into v, sigma square by 2e by 2e into v, and pr proof resilience equals to sigma y square by 2e and v, everything. Then now then come to the creep. The another concept is creep. Okay, 1 minute, I will take some water. పాస్ పెట్టించేసి Yeah, thank you. Yeah, I'll continue from the creep. So creep means, say you have a one bar, when you apply the some load, or when it is deforming, that is nothing but a delta Lx. Okay, change in lengthening along the acceleration, say. Okay, it is depends actually. If you considering vertical direction as x and horizontal direction as a z and another direction as a y, it doesn't matter. And delta Lx is a elastic deformation, and whereas red color portion is plastic deformation. Plastic deformation means if it goes to in that level, that fellow will not come back. Okay, that is only that, it's nothing but a creep actually. Okay, even in a horizontal side, if you see load p, of course here p is supposed to apply, maybe not applied here. And p, if you apply like this, delta Lx is nothing but elastic deformation, whereas delta Ly is nothing, some denotation it has been given, plastic deformation or creep. So it is the plastic deformation which occurs on the deformable body over the period of time due to dead load or statically applied load. That is the definition. It's a long process actually, creep. Factors affecting creep: temperature, homologous temperature. Homologous temperature means it is a transition temperature for creep to be tolerable or intolerable. Below homologous temperature, creep is tolerable. Above homologous temperature, creep is intolerable. Okay, so temperature is increasing, creep is also will increase. With the time, creep increases, but creep rate decreases. Creep may increases, but creep rate, what is meant by creep rate, we'll see here. You can see delta versus time. With the time, the graph is going like this, and your delta Lx, elastic deformation and plastic deformation can be seen like this. Nature of load. The nature of load is greater the magnitude of load, more the effect of creep. Heavy load if you apply, the creep effect will also more. Due to creep, stress increases, decreases, remains constant, both increases and decreases. Due to creep, stress both increases and decreases. Wrong answer. It remains constant. Stress may not change. Fatigue and endurance limit. Fatigue and endurance limit. It is failure due to dynamic loading or cyclic loading or reversal of stress. Nothing but a fatigue actually. Are you getting my point? Fatigue is a very important topic for the mechanical students because they deal with motorcycles, cars, motors, vehicles. Okay, so there repeatedly this load will come, dynamic loading and cyclic loading, reversal of stress loading. So fatigue is that one. Endurance limit. The strength for which the material need to be designed when subjected to reversal of stress. The strength for which the material need to be designed when subjected to reversal of stress. For a material, endurance limit is less than its yield strength and ultimate strength. For reversal of stress, higher factor of safety should be considered. Tensile test on mild steel, if you see here, you will understand the proportionality limits and all. Actually, as per American standard for testing machines, ASTM, on universal testing machine, mechanical people only, UTM at a cylindrical specimen, and the diameter is 0.5 inches. 0.5 inches means 12.5 centimeters. Sorry, 12.5 mm. 25 mm is 1 inch. 2.54 actually. 2.54 centimeter. 1 inch equal to. When you apply load P, the gauge length, that means if you take the specimen coupon, in the coupon, the gauge length will be decided that the gauge length is 2 inches. It's a standard. So when you test this one, that all limits, how you are getting, you can see the proof strains and all respective strains at the lower yield point D and even E point at the plateau limit, that is 15%, 15 to 20% at ultimate. Breaking point, you have a 25 to 30% of strains actually, and these are the stresses. First of all, if you see the A is proportionality limit, and B is elastic limit, and C is upper yield point, D is lower yield point, D is yield plateau. That means it will try to yield only. That means strain only will increase, and strain hardening region EF. That means it will only strain will try to harden. FG is nothing but a strain softening region or necking region. That means you try to failure actually. Then G point is the breaking stress point. OA means this is O and A. OA means metal will regain its original position. Hooke's law valid, and AB is metal will regain its original position, but Hooke's law is not valid. Because why Hooke's law is not valid? After A point, there is some zigzag portion will be there in the sigma and epsilon. And sigma and epsilon, when these two are not proportional, that means simultaneously both has to increase in same time. When it is not happening, then Hooke's law is not valid actually. Upper and lower yield point are not constant. Upper point actually not constant. Yielding start at this point, not considered for the design. Upper point cannot be considered. Lower yield point actually constant here, and considered in the design. Lower yield point only they will consider for the design. Yield plateau means material continuously deform without decreasing in stress. Strain hardening region means due to sufficient hardening of the material till E to produce further deformation, large load is required. Chale, heavy load కావాలన్నమాట దానికి డిఫార్మేషన్ పెరగడం కోసం అంత గట్టిగా ఉంటుంది. దట్ ఈస్ కాల్డ్ స్ట్రెయిన్ హార్డనింగ్ రీజన్ అంటారు దాన్ని. స్ట్రెయిన్ సాఫనింగ్ రీజన్ మీన్స్ స్లోగా పడిపోతూ ఉంటుంది. సో ఇట్ విల్ ఫార్మ్ యాజ్ ఏ వన్ కప్ అండ్ కోన్ ఫెయిల్యూర్ ఇఫ్ యూ అబ్జర్వ్ విత్ 45 degrees cup and cone failure at final at necking point. If you see the stress strain curve for different materials, okay, it is very useful one. Stress and strains, if you see, first of all, this curve actually whatever the upper and lower yield points are there, that is for mild steel. But if you see the another blue line, that is Fe415, red line is Fe500. Fe500 means TMT bar, thermomechanically treated bars. Fe500 means Fe415 means HVHD bars, high yield strength deformed bars. So, but before, if you see, here is the cast iron. That means below the Fe415 only cast iron is there. Then maybe below that you have a aluminium, cork, wood, concrete, rubber. Okay, sigma equals to Young's modulus into epsilon, and this angle actually theta. Okay, and E equals to sigma by E. That means epsilon equals to sigma by E. Young's modulus equals to stress by strain. That is nothing but a tan theta. That means theta equals to tan inverse E. So this E is coming around some 2 into 24 of 5. If you put, you are getting angle around some 89.99. That means almost 90. Okay, so that is exactly 90 degrees. It is making. Okay, then what is for steel actually it's a 2 into 24 of 5 per mm square Young's modulus. That is modulus of velocity. And for cast iron almost it is equivalent to steel load sagam untundi adi, steel divided by 2. For aluminum, steel divided by 3. Young's modulus of steel divided by 3. For wood, 1/8 to 1/15 of steel Young's modulus. For concrete, 1/10 to 1/20 of steel Young's modulus. Okay, slope of stress strain curve is nothing but Young's modulus of rigidity, elasticity. Greater the E value, more the metal will be elastic. Steel is more elastic than rubber. Steel is more elastic than rubber. And design strength for the material not showing definite yield point. Okay, not showing definite yield point, because as you know, where actually this proof strain and proof stress concept has come, because when you test any material, when it's showing the graph that P delta sigma versus strain graph, in that graph you can't find exact yield stress actually. So to identify that yield strength, there will be one tangent point has been drawn along that graph with the angle of some 45 degrees. So whatever, wherever it is touching, that is from origin point to this point, that is 0.2, that is 20% of proof strain, 20% of strain. Okay, that is nothing but a your whole strain, that is nothing but a proof strain actually. So wherever this point is touching, respect to that horizontal line is nothing but a proof stress, nothing but a design yield stress. So this is basically found by using the offset method. Majority of the people should concentrate on this point, because maybe earlier whether you heard about this or not, by using the offset method, we are exploring this point. Next, effect of carbon percentage on material property. Higher carbon percentage, ultimate strength, yield strength will be higher. Even skid resistance, wear and tear resistance, brittleness, everything will be higher. ఏమేమి డౌన్ అయిపోతాయి కార్బన్ ఎక్కువ ఉంటే? డక్టిలిటీ డౌన్ అయిపోతుంది, టఫ్నెస్ తక్కువైపోతుంది, malleability, machinability, formability. Okay. Note, tenacity is nothing but a property by virtue of which material has high tensile strength. Okay. Anyhow, that is one very good information. If carbon percentage increases, what are the properties and what is the behaviors of the materials is increasing and decreasing, you can easily observe from this description. Then in the simple stress only, stress, pressure and strength. What is the difference between these three? You can observe. What is meant by pressure? When you apply some load pressure on the with area crossing area A, pressure is nothing but a F by A. It is external normal force acting per unit area of the member. It is nothing but a pressure. Stress means with the area A again F, if you apply, it is applying again like this, and these all points, whatever the points, wherever the deformation is coming. So it is the internal resistance. Internally, some resistance is coming. Internal resistance developed in the deformable body. It has to get deformed due to externally applied load producing deformation. Okay, average stress you have to take. Average stress we have to consider. Strength of metal is studied for equilibrium object. Okay, strength of metal is studied for equilibrium object. And even if you apply the load like this, and if you cut the portion over here, whatever the average stress equals to pressure. So it is nothing but a F by A. Okay, average stress means along the whole body. So stress may be average or engineering. Strain is the cause for stress actually. Basically, strain is the cause for stress. Strength, it is a metal property. It is constant for given material. Maximum value of stress which a material can withstand without failure. It is independent of load applied and cross section area. Classification of stress: normal stress, shear stress. Perpendicular to cross section is nothing but a normal stress. In the normal stress, direct stress is there, indirect normal stress, or bending stress or flexure stress. Anything you can say. Indirect normal stress is nothing but a bending stress or flexure stress. Of course, classification I have already shown in the last class, but this will give another kind of feeling and understanding about the different types of stresses. In the direct and normal stress, you have again tensile stress and compressive stress. Sigma average is nothing but a P by A and sigma average is nothing but for suppose if you apply C here, C by A, stress remains section, and sigma average variation will be like this for this kind of loading pattern when you apply the loads like this. Okay, opposite actually. When you apply load like this, your stress will be opposite. And load applied movement will be like this, and your bending moment will form like this. Okay, your bending movement will be like indirectly it will be acting indirectly indirectly to the normal. So the bending stress always it should be like it will try to bend. Okay, it is not a normal like this. It will try to along the lateral. And variation is linear at the cross section. You can see this. Then come to the shear stress tangential to the cross section means sides. So direct shear stress ఉంటుంది ఇక్కడ, indirect shear stress ఉంటుంది. So direct stress is nothing but a normal you can observe along the four directions. It will be like a shear kind of thing. And indirect shear stress or torsion stress along the like any piston or circular cross section. If you apply the torsional movement like this, that is nothing but indirect shear stress. So now stress tensor ante stress tensor quantity or second order tensor quantity, a quantity which has one magnitude and two directions. Name example stress tensor ki one magnitude ఉంటుంది, two directions ఉంటాయి. One is stress, strain, movement of inertia. These all comes under stress tensors. Vector quantity or first order tensor, దీనికి ఏముంటుంది, one magnitude, one direction. Examples force, velocity, acceleration, movement quantity. Movement. Scalar quantity means one magnitude, no direction, zero order tensor. Example speed and distance. Okay. Stress representation. If you see the stress representation here, sigma ij is how we can represent this. I means direction perpendicular to the cross section at which stress is acting. J means direction of stress. Direction perpendicular to the cross section at which stress is acting. J means direction. Okay, that means in sigma xx it is acting in x direction. It is acting in x direction along the perpendicular to cross section. Okay, it is acting perpendicular to cross section. The direction is x only, correct? Yx, but this is tau x, tau yx. Why? Because it is shear stress. It is normal stress. If you see the x, y, z, you can observe this in what way it has come. And even stress tensor representation of all the stresses acting at a point is stress tensor. For representation, if you cut these three planes, plane 1, 2, 3. What is this plane? This plane is actually you can see this plane it is talking. It is a YZ plane, no? Then if you talk about the top plane, what is this plane? This is XZ plane, correct? This is XZ plane, correct? So top plane ante bottom plane e kada. Then what about this plane? This is nothing but a side plane, no? XY plane. So along the XY plane you have a Z direction. Along the YZ plane, ZY plane, you have a X direction, X normal. Along the X and Z plane, you have a Y normal. Okay, you can see this in all directions. What are the representation of the stresses? You can see this is number 1, and where is number 2? This is number 2. This is number 3, 4, 5, 6, 7, 8, 9. Okay, you can see these planes also. I have shown this, whatever the planes I have already explained. 3 mutually perpendicular planes are required. Each plane can carry 1 normal and 2 shear stress. So a total of stresses can act at a point. The representation of these 9 stresses in matrix form is referred as stress tensor matrix. Okay. How to represent this? Number 1 is nothing but a sigma xx accepted. Number 2 xz accepted. Number 3 sigma xy accepted. Number 4 yy accepted. Number 5 yz. Number 6 yx. Number 7 zy. 8 zx and 9 zz. So you can put all 9 stresses like this: sigma xx, yy, zz along the diagonal. These are normal stresses. Above these are shear stresses. And another thing, sigma yx or sigma xy, these two are same actually, because interchanging only, no, almost equality of the shear stresses is nothing but tau xy equals to tau yx. Okay, the same thing it has been shown here. That is what equality of shear stress. You can see the equality of shear stress. For equilibrium in 2D, summation of fx equals to 0, summation of fy equals 0, summation of moment along the z equals to 0. Okay. In 3D, how many are there for equilibrium? Summation of fx, fy, fz, summation of mx, my, and mz. And if you draw these all things, and if you start applying at O point, summation of moz equals to 0, and clockwise positive and anti-clockwise negative if you assume, and if you start doing this multiplication of stresses into distances along the AB, it is referred as a delta Z. Along the OA, it is referred as a delta X. Along the OE, it is referred as a delta Y. It is not shown here, but it is delta Y. So if you are taking summation of O Z equals to 0, if you are taking like this, and if you have to concentrate first, this one is tau xy. Why tau xy? Because it is reaching to O point into negative actually, correct? Anti-clockwise. So it has to reach like this, correct? So tau xy into delta y into delta z, both distances you have to put into delta x, okay? Because it is prismatic into delta x. If you put, then plus tau xy here is nothing but a yx actually, yx. So yx, it is plus, you can see it is tau yx, it is reaching to O point in clockwise direction only. For that, delta x into delta z you have to put first, then delta y outside equals to 0. So if you take everything together and if you cut everything, the equality of the stresses, you can see tau xy equals to tau yx, tau yz equals to tau zy, tau xz equals to tau zx. Only when planes are perpendicular. Only when planes are perpendicular, the equality of shear stress is based upon moment equilibrium principle. Moment equilibrium principle. The next concept is biaxial stress. Biaxial stress. Biaxial stress means you have only one plane, like normal stresses will be there at the both top and bottom, and even both horizontal LHS and RHS, and along that you have a shear stresses. But if you see the shear stresses are all are same. Okay, yx xy, how it is coming same, you can see. So sigma ij equals to sigma xx, tau xy, tau yx, tau x, yy is nothing but a biaxial stress. Triaxial stress is nothing but a 3 by 3 matrix. But here for biaxial stress, for representation, how many stresses you want? 4 actually. For define, only 3 is enough, no? Sigma xx and sigma yy. Sigma yx and sigma xy are both are same, equal, no? That is why for defining, 1 is reducing. So for defining, 3 is enough. And triaxial, for representation, 9 you want. For define, how many? This 3, and here actually these 3 equal to this 3, no? So that means these 3 and these 3 altogether 6 only. For defining, you need stresses. Okay, that is the triaxial stress. Next, deformation in the bar due to axial load. Deformation in the bar due to axial load. You can see this. L is the original length, and due to deformation, L plus delta. Hooke's law is valid. Sigma is proportional to strain. That means stress proportional to strain. Sigma equals to x small s into strain. P by A equals to sigma into delta by L. Correct? So delta equals to PL by A. Deformation in a rectangular bar due to self weight. So weight density gamma equals to rho into G. Assume a strip at a distance x from bottom of length dx such that load is constant over the dx length. The load is constant over the dx length. So now above the strip line, whatever the load if you apply, that is px, and even above also the same load will be there. So therefore px equals to mx into it's nothing but a load, no? Load is nothing but a mass into acceleration into gravity. So mass is nothing but a your rho into Vx. Vx means volume. Okay, density into volume. You will get mass, and G will be common, and gamma rho G is nothing but a gamma, no? Here density. Okay, so density correct. Rho is nothing but unit weight, of course. Unit weight, mass into unit weight into density into volume. Yeah, weight density. Weight density is gamma. Gamma is nothing but a rho G, and Vx is nothing but a into x. Correct? Area into x distance. So therefore, delta strip, d delta strip, that means the small strip, is nothing but a p into this one. Actually, delta equals to PL by A, you know. So in this, L is overall length. If you take small strip, actually it will become a dx, no? AE will be same, and now you are applying the d, the difference derivative at the d also, d strip. So d strip is nothing but a px dx by AE. So what is px? Delta ax into dx by AL. So integration of d delta strip equals to gamma by E. You can take it out. Correct? Gamma E, you can take it out. And if you apply the 0 to L, x, for x, if you apply the 0 to L, you are getting delta equals to gamma by x square by L. That is 0 to L. So delta equals to gamma L square by 2E. This is used for comparison purpose. This is basically we use for comparison purpose. Now, if weight of the bar W, gamma into V, gamma into AL, if you take gamma equals to W by AL. Now delta, if you put in the wherever gamma is coming, delta by AL, if you put, and L square by 2E if you put, and delta equals to WL by 2AE. Not used for any component. This is actually, it will not use for any component actually. And deformation in conical bar due to self-weight, if you see, again the same thing, AX is this strip area, and px and above px is there, and dx is the depth of the strip. Px equals to mx into g, and rho into vx g, rho into ax into g into why this is 1/3, because the area of the conical shape is nothing but a 1/3 into bh actually, 1/3 into bh. So what is there here? So x is their height, and this strip is also px actually. So that has been taken 1/3 into bh is the area of the conical shape. That means your triangle area is half into bh, whereas your uh, what is parabola kind of curve, you have a 1/3 into bh. So based on that, again d delta strip, if you take px into dx into divided by ax e, if you take this same thing, whatever I have done at the top portion can be applied here, and finally delta equals to gamma l square by 6 ee you are getting. And if weight of the bar w gamma into v is nothing but a gamma into volume is nothing but a 1/3 of al. Okay, whatever that I told no. So area of the tunnel also you can take. So gamma al by 3, and gamma equals to 3w by al, and delta equals to 3w by al into l square by 6e, and finally wl by 2al. And deformation rectangular bar due to self-weight is, and deformation conical bar due to self-weight is, if you both cancel everything, you are getting 3 is the ratio. And deformation in tapered circular rod due to axial load. Because why I am importantly explaining this, dear students, especially mechanical students, this kind of questions repeatedly they are asking in GATE or in any competitive exam. Even for civil students also, there will be a chance of up to like rectangle, maybe tapered and conical may not come for them, but up to rectangular for them it is most important. Please have a look on this, which I am explaining. Even see, when I am explaining, by listening you can take the photos. Even I am ready to provide the material. Even madam people has to give instruction to me who are organizing this. If they give instructions immediately, I am ready to share this PPT so that it will help you all for preparation with your own after explaining by myself the concept, the exact concept. Okay. Then deformation in tapered circular rod due to axial load, delta equals to PL by AE, whatever that is, and delta strip equals to P dx by AX into A. Same thing, but AX equals to pi d square by 4 into dx square into E. Like this you are getting, and at x equals to 0, dx is d1 only, correct? At x equals to L, dx equals to d2, correct? For 0 to L, delta dx equals to d1 minus d2. For 1 meter, delta dx equals to d1 by d2 by L, correct? Per meter length తీసుకుంటారు. That is only, no. For x, delta dx equals to d1 by minus d2 by L into x, correct? For x distance. At x equals to x, dx equals to that means d1 minus kx. Kx is integration operator. When you're integrating this, you will get the integration operator like this. Okay. Then delta dx equals to kx. Okay, if you are removing this d1 also, and delta dx equals to kx you are getting. So integration of the d delta strip, whatever you got above that, and now d1 minus kx square if you put in the place of dx, then you are finally, after doing the integration and all, you are getting like these denominators and numerators, and finally your delta equals to 4pl by pi ed d1. Okay. Okay. Otherwise we can write delta equals to like this also. Okay. This 4 has went upward because of this is in denominator here. Okay. I hope you understood this. and deformation in tapered rectangular bar due to axial load can be seen here. And the same way you can observe this, but here the bx is b1 plus kx. Okay, how it has come? Again, ax equal to bx into t. Ax is the area of the strip, and dx is the depth of strip. X equals to 0, bx equals to b1, x equals to l, bx equals to b2, whereas 0 to l equal to delta bx, nothing but a b2 minus b1. For 1 meter length, delta bx equals to b2 minus b1 by l. For x meters, delta bx equals to b2 minus b1 by l into x. So delta bx equals to kx, whatever the same thing I have done there. So d delta strip equals to same formula, and finally you are getting, this is in ln actually. So okay, ln you supposed to apply. Why it has come ln? You can see this by seeing this expression. Delta equals to p by te into l by b2 minus b1 into ln b2 minus b2 by b1 equals to p into l by b2 minus b1 into t into e ln b2 by b1. Okay. So like this, once you know the derivative parts of the different shapes, now it is very easy to understand the another type of problems, to know the to calculate the stresses and even deformations like that. There is a one question, gate question actually. For the bar shown in the figure, if cross section area is 5 centimeter square and Young's modulus E equals to 200 GPa, then determine the deformation in the bar. Okay, deformation in the bar. So first of all, you have a system like this, A, B, C, D like this, and the distances from A to B is 1 meter and B to C is 2 meters, whereas C to D is 1 meter, and you have the forces like this outside A at A and at D. You have applied the loads. One is outside and it is towards D inside. So now summation of Fx equals to 0 means 60 minus 60 equals to 0, correct? At all forces. This is 15. This is also 45. Now this is 35 plus 25. So altogether it is coming 0. So it is an equilibrium actually. Now you can apply the conventional approach. But before that, you can draw the free body diagram. Free body diagram, of course, from here you can draw. For a conventional approach, what you can do, you can divide into number of strips actually wherever cuttings are there, and you can make it into, this is also one part and another part, and wherever you cut it, and this is third part and fourth part and fifth part, and wherever you cut it, these are like a distance of dx and dx, and now this distances remain same, and all forces whatever there have been applied here. And now if you separate into all parts into separate way FBD, for balancing you can see for part 1 15 is here, and for balancing purpose another 15 you supposed to apply that side, correct? And here for the this strip, this is 15 again here. For opposite to balancing this one, again you have to apply another 15 here, and but 35 it is going that side. To balancing that one, already 15 is there here, and out of 15, out of 35, you must remove this 15, correct? Correct, to balancing this one. So 35 minus 25, 20 you supposed to apply again opposite to that. Then only the 35 will be balanced there. That means along the 15, whatever I shown here, you can see this. Yeah, I can take the laser point over here. Yeah, this 15, whatever it is there, to balancing that one, opposite to 35, you must apply one more 20 only, then only it will get balanced. Okay, then whatever this 20 is there, you must apply this here 20, and again opposite to that, again you have to apply one more 20. But here this 25 is applying, and for applying 25, for applying here 25 is applying, but here actually 20 is applying oppositely, no? So here to balancing that, again here one more 20 you must supposed to apply. But here what is happening, for 25 and 20 total, how much total together? 45. To balancing that one, again 45 you have to apply, and of course opposite that 45 you have to apply, and finally there is a 45. I hope you understood this. Okay, Yeah, I'll draw the pen. You can see this position may be clumsy. I can draw and I can show you. This is 15, correct? To balancing that one, మీరు ఇక్కడ 15 అప్లై చేయాలి, కరెక్ట్ అంతేనా? మళ్ళీ దీనికి బ్యాలెన్స్ చేసుకోవడం కోసం మళ్ళీ చిన్న స్ట్రిప్ దాన్ని ఆనుకొని ఉంది కదా సెకండ్ స్ట్రిప్, దానికి మళ్ళీ మీరు 15 ఆపోజిట్ అప్లై చేయాలి కదా. కానీ దీనికి మధ్యలో ఇలాగా 35 ఉంది, కరెక్ట్? సో ఇప్పుడు ఆల్రెడీ 15 ఉంది ఇక్కడ, ఈ 35ని చేయాలంటే ఇంకొక 20 ఇక్కడ అప్లై చేస్తేనే కదా ఇది మొత్తం 35కి ఆపోజిట్ అవుతుంది. దిస్ ఈస్ పార్ట్ 2 అన్నమాట. ఇది నెంబర్ 1. అర్థమైందా అండి? సో ఇప్పుడు ఈ థర్డ్ పోర్షన్ తీసుకుందాం. థర్డ్ పోర్షన్ కొంచెం పెద్దగా తీసుకుందాం. సో థర్డ్ పోర్షన్ కి ఆల్రెడీ ఏముంది, ఏం అప్లై చేయాలి? ఇప్పుడు 20 ఆపోజిట్ ఉందంటే ఇక్కడ 20 అప్లై చేయాలి, కరెక్ట్? అంతే కదా, 20 వెళ్తుందంటే 20 ఆపోజిట్ అప్లై చేయాలి. సో when you are applying 20 opposite and another 20 also is supposed to apply here opposite here, another side 20 అప్లై చేయాలి. ఓకే, సో మళ్ళీ ఫోర్త్ స్టెప్ చూసుకోండి. ఇక్కడ ఫోర్త్ స్టెప్ చూపిస్తాను. ఇది థర్డ్ వన్, దిస్ ఇస్ 4. ఫర్ ఫోర్త్ స్టెప్ ఇప్పుడు ఇక్కడ 20 అప్లై చేశారంటే ఆపోజిట్ కి 20 అప్లై చేశారంటే ఫోర్త్ స్టెప్ థర్డ్ కి యాక్చువల్ గా 20 ఆపోజిట్ కి అప్లై చేసాం. ఫోర్త్ స్టెప్ కి ఇక్కడ అబ్వియస్ గా మీరు ఆపోజిట్ లో 20 అప్లై చేయాలి. ఎందుకు? ఇది ఇలా ఉల్టా ఉంది కాబట్టి 20 మీరు ఇక్కడ ఆపోజిట్ అప్లై చేయాలి. సో ఇక్కడ 20 ఉంది, ఆల్రెడీ 25 ఈ డైరెక్షన్ లోనే ఉంది. సో ఈ 25ని 20ని బ్యాలెన్స్ చేయాలంటే ఆపోజిట్ హౌ మచ్ యూ సపోజ్ టు అప్లై అగైన్ హియర్ 45. సో ఈ 45ని బ్యాలెన్స్ చేయాలంటే ఇక్కడ 5th స్టెప్ చూపిస్తాను, చూడండి. ఈ 45ని మీరు ఆపోజిట్ గా అప్లై చేయాలంటే ఇటు సైడ్ 45 అప్లై చేయాల్సిందే, అంతే కదా. అండ్ ఈ 45 ఆపోజిట్ లో ఆల్రెడీ ఇక్కడ 45 ఉంది, బై ప్రాబ్లం లోనే ఉంది, కరెక్ట్? ఇది బ్యాలెన్సింగ్ చేయడం అంటేనండి. హౌ టు బ్యాలెన్స్ ద లోడ్స్ యూ కెన్ సీ ఫ్రమ్ ది నెంబర్ 1, 2, 3, 4, 5. I hope you understood this. I hope you understood this. I hope you understood this. Okay. Like this, I would like to go forward. Now, objective approach, if you see this, the continuity of that. So 1, 2, 3 like that, and how it has been applied, everything you can see this, the balancing, whatever I applied you, shown you. Tensile actually it's a elongation, you try to take positive, and compression, it is a compressive load compression, it will shrink actually, it's a minus you take. So therefore delta AD and total whatever delta AD is there from A to D is nothing but a sigma AB plus delta AB plus delta BC plus delta CD only, correct? So it is nothing but a P1 L1 by AE, P2 L2 by AE, P3 L3 by AE, correct? So 1 by AE if you take out, what is P1? So 15 actually, correct? It's a 15. It's a tensile, no? Tensile, you take plus. And next P2, P2 ఏంటి balancing 20 కదా. So 20 ఏంటి compressive లో ఉంది, 20 compression లో ఉంది. So 20 compression can be taken as a minus into what is the distance 2, and here again 45 also compression, that is minus 45 into one distance. So altogether if you calculate, area equals to 5 centimeter square and E equals to 200 GPa. Yeah, so if you convert everything into this, 200 into 10 to the power of 3 20 per mm square, AE equals to, you are getting value like this, and sigma AD equals to, all together if you put and you are getting the values like this, finally sigma AD equals to minus 0.7 mm. Okay, so minus is nothing but a compressive displacement there. It is getting compressive. And draw the axial thrust diagram. For this problem only, they may ask sometimes to draw the axial thrust diagrams. Okay, so you can see this first of all. So tensile 15, you can draw plus, and up to next the 35 is there. So 35 means how it will go. It has to go to 15 already covered here, and the remaining the 20 will be minus because it is a compression. And again 20 plus 25, it is getting increasing in the form of compression only. So you can draw that is in 45 minus, and again 45 here again compression. You can draw that is into all the minus place. For suppose if it is outside away, this fellow will go in positive side. Actually it will go in positive side. Okay, so left to right, area at right away from area, tensile positive towards the area, compression, maximum tensile force. How to find out maximum tensile force? Maximum tensile force, how to find out? Whatever 15 is their top, divided by area. So 5 kilonewton divided by 5 centimeter square, 3 kilonewton per cm square. Maximum compressive stress can be calculated 45 divided by 5. That is 9 kilonewton per centimeter square. Okay. So for the fixed bar shown in the figure, determine the support reaction and also draw the axial thrust diagram. A is constant. Okay, so summation of Fx equals to 0, both LHS to RHS plus and RHS to LHS minus. So minus RA plus P plus 2P minus RD equals to 0. So from there equilibrium equation, we can calculate RA plus RD, and RD also can be calculated. Now how to apply the free body diagram? The all components, RP, RD, everything similar to the previous problem, and the summation of AD equals to like this. You can find, because why summation of AD equals to like this 0? Because it's a fixed thing, no? Fixed thing. In the previous problem, it is not fixed. The loads are there. That is why delta AD equals to these all things. Whereas delta AD equals to these all things. Now it is equals to 0. So by using this expression, you can find out and always make it into 0, and finally RA you can get it, because this is nothing but a statically indeterminate structure. The unknowns, 2 equations only you have, but another equation you supposed to get by applying the some compatibility conditions. That compatibility condition is this only. Summation of AD equals to 0 at the supports, at the both supports, because fixed supports cannot deform, no? So based on that, you can find out and you can draw the axial thrust diagram also similar way what I have shown there. And 4P by 3, because this is RA, and even you are getting RD also here like this, and whatever the RD RBs you are getting, you can draw the based on the diagrams. 4P by 3, then after that P minus 4P by 3, whatever you are getting, P by 3. Then after P by 3 again you have to add the 2P. So P by 3 plus 2P, if you add 5P by 3 you are getting. So that you can see here. Okay, so 5P by 3 you can draw here once again. So then again 5P by 3 balance. So like that you can do this kind of problems also. Sometimes for creating disturbance, for creating some thinking thinking from your end is very higher way, so they may give this kind of questions. And you can see the one more question for the rigid body attached to the cable as shown in the figure. Determine the tensile force in the cable. A and B cables are attached to fixed support at the like this, and rigid beam is like this, and there is a one hinge support. And from wherever the load is applying at the center, the equal distance is distributing that L by 2, L by 2, delta B by B. The distance is actually, so from A to this one is A, and B to this hinge is B actually. I have not shown here. You can see this. I have shown here. So therefore, there is a similar triangle kind of thing. So delta B by B equals to delta A by A equals to tan theta. So what is delta B by B? Even this one you can write.
I did not understand.
Hello? Someone is talking. Suma? Suma. Yeah, speak out. Suma?
Yes, sir.
Yeah, is it okay? Shall I go ahead?
Yes, sir.
Any doubts for the students?
No, sir. If they have any doubts, they will give you reply in chat box, sir.
Let us take 5 to 10 minutes chat questions also if they have anything. Yeah, like this way you can calculate. Of course, this kind of problem you might have seen in the engineering mechanics. Delta A, delta B, how it is, and theta. And TB is nothing but tension in B cable. So that can be found like this. And again now summation of at hinge equals to 0. Moment. Summation of moments at hinge equals to 0 if you take. And finally if you find TA into A, distances TB into B minus P into L by 2 equals to 0. And finally TA and TB you are getting it. How to find out the T and TB, you can easily find from this numerical. So for the beam spring system shown in the figure, determine the ratio of the forces on the spring FA, FB, FC. The ratios are actually given A, B, C, D like this. This is also one of the gate question given for civil people only. So there are distances like from this cable, from hinge point to first cable A, second cable 2A, and third cable 3A, and rigid beam is there, and the center wherever load is applying, the distance is L by 2, and this remaining distance also L by 2. the ratios are 1:4:9, and 9:4:1, and 1:1:1, and none of these. How to do this directly? So wherever the things are coming A, 2A, 3A, and delta B, and delta C, and theta. So tan theta equals to delta C by A, and equals to delta B by 2A, and delta C, A by 3A, correct? So how we can do this? This is nothing but a C. E will be same, and delta is nothing but a for the force by K, and even force by 2K, and even force A by 3K. And now if you cancel everything, finally you are getting the ratios of FA equals to FB equals to FC equals to 9, 4, 1. Okay. So like that you can find out the ratios by for the different type of problems. Once again you can come back. These are the problems. You can see gate oriented problem. Okay. Next, strain energy. Once again, it is explaining here. gradual load. There are so many type of strain energies for the different type of loads. Gradual load, it is the load which is applied slowly at a certain rate. You can see P delta is PL by AE and U equals to half into P into delta, P into PL by AE, P square L by 2AE, P square L by 2AE. How to find out the U, the strain energy, and U equals to if it is P by 2, P by 2 పోయిందా లేదా గుర్తుకుందండి అది గుర్తుకుంది పోలా. So how to get these all formulas you have seen in the previously. Of course, this I have already shown for the gradual load. For sudden load, if you see the delta equals to 2 PL by AE. Okay, the delta equals to 2 PL by AE because the area you can see U into P delta only, because it is not triangle, it's a rectangle. You have a 2 P into delta. So P into 2 PL by AE, you can put whatever the delta is there, and by calculating everything, then finally stress can be calculated 2P by A, and finally U equals to delta square AE by 2L. That is for sudden load. And note, compared to gradual load, in sudden load, deformation and stress are 2 times, strain is 4 times. Okay, compared to sudden load and gradual load. Impact load. Impact load means if you see this, there will be a there will be a area of the cross section, and the bar is like this, and the distance is L, and this is H is nothing but you have a like elastic deformation, and W is nothing but plastic deformation, for suppose if you say, and external work done equals to strain energy. How to find out the external work done? W into H plus delta, okay, and equals to delta square AE by 2L, because impact load is nothing but a sudden load, no? So that delta static load, delta static load is nothing but a PL by AE. So delta equals to, if H equals to 0, delta equals to 2 delta static, that is nothing but a 2 PL by AE. This is for sudden load. So delta equals to sigma static, delta static plus root of delta static square plus 2 into H into delta static. Okay, if you want to find out the main delta for the impact load, so that is nothing but a sigma equals to delta W by A into 1 plus root of 1 plus 2 into H by sigma static. Okay, anyhow, that is for the impact load. You can observe this, how the impact load is applied and how the your deformations are coming there. Okay, next, superposition principle. If load is within proportionality limit and stress function like shear force, bending moment, twisting moment, angle of twist, slope, deflection, etc., varies linear with the load applied, then the effect of multiple loading at a point is same as summation of effect of individual loading at the same point. That means P1, P2, even as it is, I have shown this, how the superposition is valid. Superposition principle cannot be applied to the strain energy. Why superposition principle cannot be applied to the strain energy? Because stress is proportional to strain and it obeys the Hooke's law, but in the strain energy concept, the things are differently coming. You can see here the formula, everything finally we're getting differently. So that is why the superposition principle cannot be applied to the strain energy. Strain equals to change in length by initial length, a quantity which gives the intensity of internal deformation. Normal strain, shear strain. So normal strain is Basically you can see when you apply the load with the dimension of B, L and L by L plus delta, due to normal strain, shape remains constant but size changes. This process is referred as dilation. Okay, shear strain ante this angle is nothing but a shear strain. Due to shear strain, shape changes but size remains constant. This process is referred as distortion. Okay, you understood the difference between normal strain and shear strain? Distortion and dilation. Okay, shear strain can be seen here like this, how it is acting along the x and y direction. Complementary shear is automatically coming when you are applying this stress only. This yx actually similar to xy, correct? How it is coming? It is a complementary. These are you applied, but these are automatically developing. Okay, these are nothing but a complementary shear. This is applied shear. So you can see applied shear plus complementary shear is coming as a shear strain actually, both. And you can see for suppose if it is making with gamma xy means shear strain it is making, and you are applying a shear stresses. Due to the shear stresses, this body is creating some shear strain over here. Okay, but when you are applying the complementary shear stress, the shear strain will be developing along the vertical direction. Okay, see gamma xy shear gamma xy shear strain produced only due to tau xy. Okay, shear strain this is actually gamma xy. You can take gamma xy is producing due to tau xy, and gamma yx shear strain produced only due to tau yx. And for suppose you have a gamma xy and gamma yx on both along horizontal and vertical direction, your internal angle is nothing but a pi by 2 is nothing but a 90. No, 90 minus pi xy. So pi xy is nothing but a gamma xy plus gamma yx equals to shear strain produced due to combination of tau xy and tau yx. Okay, it is a combination of both. Combination of pi xy is nothing but a combination of both shear strains. Okay, shear stresses. So shear strain equals to tau xy equals to tau yx equals to equality of shear stress. Gamma xy equals to gamma yx, and gamma xy equals to 2 times of gamma yx. No, otherwise 2 times of gamma yx. Correct, as per previous question. And shear modulus of rigidity is nothing but a GRC. Shear modulus is nothing but a shear stress by shear strain. So shear strain is tau xy by gamma xy. Tau xy by gamma xy. So sign convention for shear strain is if you have the diagram like this on plane is like this, 90 minus gamma xy. Gamma xy pi xy is nothing but a combination of both gamma xy and gamma yx. Correct? Or gamma xy and gamma yx is both are same. So this one you can write minus 2 into gamma yx or gamma xy. So whatever I have written here. So this is positive way. You can see this. For suppose you have a plane, another plane like this, you must add 90 minus this gamma xy, sorry, pi xy. So this is actually negative time. You have to use like this. Negative time you have to use like this. So strain tensor, if you see, representation of state strain at a point. After explaining this, I will stop here and I will try to take the questions and I will wind up the session. Strain tensor, you can see how to write a strain tensor similar to stress tensor. Epsilon xx, gamma xy, these are actually shear strains. These are normal strains. Correct? Normal strains. But gamma xy can be written because sigma xy equals to 2 into gamma xy. So gamma xy can be written pi xy by 2, pi xy by 2, pi xz by 2. Are you getting my point? From here you can take my laser point where it is rotating. You can see from this you can write this gamma xy can be written as a pi xy by 2, pi xy by 2. Like this you can write the straight tensor. Okay. So with this I'm closing here, and I will continue in the remaining part in the next class, and even in the next class I will try to see the few important gate questions also. Of course I am already combination of the concept as well as gate questions I am seeing, and I will try to show the gate material which is providing by AS coaching center also in the next class. So thanks for bearing with me for this gate classes. Yeah, sir, can you share these notes? Please, can you explain about the first point? First point means Raghunath Nemali. Can you ask the Raghunath Nemali what is your first point meaning?
Sir, it is starting class, sir. Assumptions of
Assumptions of this today's class?
initial
ఏమండి? Huh?
starting లో క్వశ్చన్ సార్ అది.
Starting off, okay. Let me go back. This is the this one? Assumptions in the strength of material.
Yes, sir, first assumption. Continue.
Yeah. The body is deformable means it should be deformable. That means it should not be a rigid body. It should be a deformable body. That means when you apply the external load, the molecules from one place to another place, it has to shift. Then only the strength of metal is applicable. So that body, what are the bodies are there? Like bar you take, it is deformable. Like ductility metal you take, it is deformable. But if you take any stone or any rock, it is not a deformable body. It is a rigid body. Suddenly it will fail. Okay, but there are some deformable bodies. Like if you take the concrete, it's a deformable body, but it is a brittle nature of the material actually. So that is I wanted to explain. And continuous means the material molecules, whatever it is there, like in the steel, if you take, it is a continuously the same molecules will be there. But in the market actually, if you see whatever the reinforcement bars they are using for the construction, if you are a mechanical students or civil students, both can understand this. 12 meters available actually. Vizag steel, from the Vizag steel plant, if you order the steel, 12 meters it is available. At 12 meters actually it should be continuous. It should not be a discontinuous material. It should be continuous along the whole part. For suppose you have a 1 meter length of the material, it should be continuous. మధ్యలో ఒక 500 mm అంటే 0.5 meters అయిపోయిన తర్వాత ఏదో సమ్ డిస్కంటిన్యూటీగా ఏదో సమ్ హింజ్ ఉండి అక్కడ హింజ్ ఉండి మళ్ళీ కంటిన్యూ అయింది అనుకోండి, అది కంటిన్యూస్ కాదు. అలాగా ఉండకూడదు, మెటీరియల్ కంటిన్యూస్ గా ఉండాలి. దట్ ఈస్ ద మీనింగ్ ఆఫ్ డిఫార్మబుల్ అండ్ కంటిన్యూస్. క్లియర్? ఇస్ ఇట్ క్లియర్ అంటే? రఘునాథ్ yeah. See, I will share this document. Thanks for attending this GATE classes. Please, once again, I'm informing that please inform to your friends also. Ask them to come and join these GATE classes and make use of this opportunity. We are in the initial stages only still. Of course, I am ready to share this document to the organizers of maybe Madam Suma or Dr. Lakshmi Keshav Madam, who is the main person organizing this GATE classes for the all departments, not only civil and mechanical, the all departments in the entire college under the Prerna. I'll try to forward to them and they will try to forward to you all. Is it okay? Okay. With this, I'm winding up this class. So thanks once again for attending the GATE classes. Yeah, if anything is there, of course, my number also I can type it in the chat box. This is my number. You can WhatsApp with me about your gate doubts like pattern of the paper, strategies, how to prepare, how to collect the material for both mechanical and civil. Irrespective of the strength of metal subject, I am ready to help another ideas also how to prepare and what is the weightage of the different papers, and even so apply the strategy plan. The first day, first class, if you might have attended, I hope you might have understood the way of explanation about the strategy, how to prepare for the gate examination, and even the questions you are expecting in the gate examination. Even percentage of the marks, how much you are expecting, you might have understood. Even in addition to that, when I'm going to sharing this document, in the document everything is there, like which I prepared, my running notes and previous questions, get previous questions captured paper, captured screenshots. So from that, additionally you can prepare so that there is a chance of cracking the gate rank. Okay, for you all, I'm telling you, it is not particularly mentioning. You have a one another advantage also like reservation. So that is also you make use of advantage and prepare well and get the many number of ranks. Okay. So with this, I would like to wind up today's class. Thank you one and all. Suma,
Thank
I'm
you,
leaving.
sir. Yes, sir. Thank you, sir.
Yeah,
Thank you, sir.
yeah, thank you.